Hello, everyone. You are welcome to today's lesson. And in today's lesson, we are going to look at our first lesson, elective math lesson for that matter, on sequences and series. Sequences and series. So what we did this morning, okay, with respect to the core maths, we are going to build on that. Okay, so by the end of this lesson, today's meeting, and even the entire lessons onward, this particular topic, sequences and series or series, please take note. Okay, these are the lesson objectives. You should know, okay, what sequences and series are and all the related concepts. Okay, all the concepts related to sequences and series. Okay, and you should also know, okay, how to find the sum to infinity. So you should know how to quote the formula for sum to infinity, and you should know how to use the formula to find the sum to infinity. And you should be able to establish the relationship between, okay, the end term of a sequence and the sum of the first end terms. So this morning we did the notations. I will briefly talk about that as and when we meet the notation, especially for those who couldn't join us, okay, this morning, so that they can, okay, easily relate as well and be in sync with whatever that I would say. Okay, so that will be the lesson objective. So I'm going to go strictly to the sum to infinity of a GP. So remember this morning, we didn't do the geometric progression. Okay, no issues. I can still explain for you to get it. Okay, we said for arithmetic progression, which is the first type of sequences and series that we dealt with. We said each term after the first term, okay, differs by a particular constant. And that constant is what we call the common difference. However, okay, in a GP, okay, instead of us to have a common difference, we have a common ratio. And whenever we mention ratio, what comes to mind?
Fraction.
Okay, fraction, very good. A number over another number, a quantity over another quantity. So whereas we said in an AP, okay, this morning we said an AP for you to get your common difference. So meaning all your terms. So I am going to, because I didn't teach you, okay, that's why I'm saying all this. Other than that, I would have moved on to this straight away. So assuming I have a sequence, okay, which will be numbers with a particular rule. Okay, and these are the numbers, and the numbers we said are called, okay, terms of the sequence. So I'm labeling the terms, and the terms of the sequence usually are denoted by U subs. So I have U sub 1 up to U sub 4. Okay, this will be my sequence. Okay, in terms of an AP, okay, we said you are supposed to get a common difference, D, and the D we said will be equal to U sub 2 minus U sub 1, which should be equal to U sub 3 minus U sub 2, okay, which should be equal to, okay, U sub 4 minus U sub 3, okay, and in general, it should be equal to U sub n minus, okay, minus U sub n minus 1, sub n minus 1. However, for a GP, we are not looking at what's difference, we are looking at ratio. Okay, so instead of dividing, instead of subtracting for that of an AP, okay, for a GP, we are going to divide. So this time, right, to be your U sub 2 should be equal to U sub 1. Okay, then your U sub 3 should be equal over U sub what? U sub 2 over U sub 1 should be equal to U sub 3 over U sub 2. And likewise, U sub 4 over, okay, U sub 3 must be equal to, and in general, our U sub n, okay, over U sub n minus 1. So for the AP, we find the difference between consecutive terms. And if the difference is uniform, is definite, okay, then it means, or it's a constant, okay, then we call it what? A common difference, or it's common. However, here you find ratios of consecutive terms after your first term. So in this case, if your ratios, they give you the same value, okay, or a uniform value or a constant, then we call it a common ratio R. So any GP, this will be a situation. Okay, so now you should be able to identify a GP. Okay, and just as you know how to identify, okay, a sequence that is an AP. Okay, so GP will be geometric progression. Remember, I mentioned it, okay, today in class when we're looking at the types of sequences that I said we will cover. Okay, so this is it. The sum to infinity, also remember this morning, I gave you as one of the notations. I mentioned this, and you know that is the infinity symbol. And this is the sum symbol, S for sum, S for sum. So usually we use a capital letter, okay, for the S. Okay, and like the other one to the U, okay, the number of terms or the general term, I said we can use a capital S or small, sorry, capital U or small u. Here, strictly, usually we use capital S. And that's not to say that if you use small x, we'll mark you down. Okay, take note. So this is the formula. And unfortunately, okay, I mean, it's not necessary for me to prove this formula, we can prove. So maybe in school, your teachers will do that. But what I'm going to do, I will throw the formula at you, okay, teach you how to put or learn, okay, to memorize the formula, and the formula will be familiar. Then after that, how best to apply the formula in dealing with what question. So this is sum to infinity is always equal to A, which is the first term over 1 minus R, where R is the common ratio. You know this notation. So here, for the sum to infinity to exist, take note, for sum to infinity to exist for a GP, and sum to infinity will not exist for an AP. For AP, you cannot find a sum to infinity. So sum to infinity is really for a GP. Even for a GP, not all GPs will have sum to infinity. Not all GPs will have sum to infinity possible. So for the sum to infinity to be possible, this condition is very vital. Your common ratio must be between -1 and 1. Okay, -1 exclusive, +1 exclusive. Take notes. Okay, so if your R is outside the range that you've been given here for R, then it means your sum to infinity will not be possible. In other words, okay, the statement that you have here, mathematically, in simple form, we put it this way. Absolute value of R should be less than 1. So when you find your common ratio, okay, and you take the absolute value of the common ratio, and you realize that the absolute value is less than 1, then it means you can find the sum to infinity of that sequence that gave you the common ratio. If the common ratio absolute value of that is greater than or equal to 1, then it means the sum to infinity will not be possible. Okay, so quickly, maybe you cannot relate very well with whatever I've said. So let's come to how practical, okay, I can explain that. So let's look at the first word example. Find the sum to infinity. So we are finding the sum to infinity. So we underline of the following, if possible. Of the following, if possible. And the sequences that you are given here, okay, obviously you can see that these are sequences. The sequences that you are given here, take notes. Okay, they are all GPs. So we'll verify whether they are GPs, just as we know how to determine an AP. We'll know how to determine that of what a GP. In combat, we'll treat that. Okay, so here I just need you to know how to determine, okay, that the sequence is a GP. Once it's a GP, okay, you put the formula for sum to infinity. And if you are able to, because for you to determine that what you have there is a GP, we will find our R. So when you get your R to satisfy the condition for you to find the sum to infinity, or the sum to infinity to be possible, then you go and find it. Otherwise, we state that it is not possible. So quickly, let's go and look at the solution. Okay, so as usual, when you read question, you underline the Salient part. What am I looking for? Sum to infinity. Okay, of the following sequences. So these are sequences, if possible. So questions are numbered because we want you to number your solution. The first thing that you write here is solution, which is already typed. So after that, questions are numbered. We want you to number your solution. So the major question number is 1. The minor question number is A. Then we extract what we are giving. So maybe giving, or you can choose not to write the giving, but the sequence you have to extract. So 27, 18, okay, 12, okay, then ellipse. So this is the sequence. Now we need to verify whether the sequence that we have there is a GP. Okay, if it's a GP, then it means it is likely we can find it was sum to infinity. Okay, remember I just told you that not all GPs, Okay, as for APs, none of them will have sum to infinity. Okay, but for a GP, some of them will have sum to infinity possible, others will not have. So let's see. For you to determine the type of sequence here we are looking at, obviously, let's test whether that's an AP. Okay, so let's find the first difference. 18 minus 27, what will you get? Hello, 18 minus 27 will give us minus
9.
minus 9. Okay, so let's look at the second pair. Okay, the difference, 12 minus 18. Obviously minus 6. So we can see that the sequence here is not an AP. So now we are going to move to that of a GP. Okay, our basic progressions, AP then GP. So let's take for GP, we are going to divide. So our second term, which is 18 over 27, what would this give you?
2 over 3.
Come again.
2 over 3.
Okay, so 2 over 3. Okay, then let's go to the next one. Okay, which will be this pair. So we are going to get 12 over 18. What would that give you?
2 over 3.
2 over 3. So now we form the ratio of consecutive terms. Okay, now let's see whether the ratio common 2 over 3, 2 over 3. So we have a common ratio. So it means we can call this R. Is that clear?
Yes, please.
Okay, so we know that what we have there is a GP. Okay, however, let's find out whether the sum to infinity will be possible. If the sum to infinity will be possible, then the absolute value of our R, remember our R is equal to what? 2 over 3. So absolute value of that will be absolute value of this. So you know every positive number, absolute value of that will come out as positive. So that will give us 2 on 3. Is that clear? You know, you understand the concept of absolute value. Right. Yes. Okay. So this will give you, is 2 over 3 less than 1?
Yes, please. Yes,
It is. So it means it satisfies the condition for the sum to infinity to be possible. Am I right? Let's go and look at the condition. Remember, we said the absolute value should be less than 1. Otherwise, the sum to infinity will not be possible. So now we can see that the absolute value is what? Less than 1. So the sum to infinity will be possible. So in this case, I will come and write, okay, sum to infinity, I will quote the formula, will be equal to, okay, we said it will be A, which is our first term, over 1 minus R, where R is our common ratio. Okay, but in this sequence, we need to find our A. Who can tell me what the A is? I want someone to tell me what the value of A will be. A, remember we said, is the first term. So in this sequence, what is the first term? Okay, Prof. Karen.
27.
27. So this is the first term, this is the second term. So A will be equal to 27. Okay, and we need our R2. And R will be equal to, remember, R is 2 on 3. Okay, this is your rough work. You shouldn't interfere. So you pack it up. Once you know your A and you know your R, you know your sum to infinity. So all right, therefore, my sum to infinity, okay, will be equal to A, which is 27, over 1 minus what? My R, which is 2 on 3. So the rest will just be algebra. You keep your 27, so it will be 27. Okay, then divided by, so I can change it to the division symbol, the bar to the symbol, because I'll write this as a central fraction. But here, this is relative math. So it's relative math, you can use your calculator to find this straight away. I'm talking about only the denominator, not the whole of this. Is my point well made? So use your calculator to find this rather than going to take the LCM. So give me the value of this.
1 on 3.
Okay, so you get 1 on 3, which in effect gives us what? 27 times what? 3, am I right?
Yes.
Okay, and that gives you?
81.
Come again.
81.
81. Remember, we've already drawn our conclusion. So therefore, the sum to infinity of this sequence will give us 81. So it means, okay, the more terms that you introduce, as you introduce and you keep on adding, Okay, the terms there, the sum will approach 81. So we'll converge or we'll move towards 81. That is the meaning. So it's only convergence sequence. I don't want to talk much about that. Convergence sequence means the sequence, if you sum, it will move towards a particular value. Divergence, especially the science students, okay, even the core science students, you should know divergence mirror and convergence mirror. Okay, you know. So divergence means it's moving away from a particular point. Convergent means it's moving towards. So in this case, your sequence must be convergent. Then it means it will move towards 81, the sum. Okay, so you have a particular sum to infinity. Okay, is my point well made? The first example is the explanation. Okay, my professors.
Yes, please.
Okay, so if your understanding is not up there, don't worry, we have more here to do. I'm very sure maybe by the time you do the next two, examples, your understanding will be perfect. So let's go and look at the second example. So I'm going to look at that of the B. Okay, so B. Okay, what sequence are we giving? I can choose not to write giving, but I have to extract my sequence. So 2, 1 over 2, okay, 1 over 8. Okay, then the ellipsis. Okay, so let's check whether, okay, obviously this is not an AP. Okay, so let's look at whether it is a GP. So if it's a GP, this time around, unfortunately, our terms, some of them are not pretty fractions, but don't worry, fortunately, we know how to deal with fractions. So you can even use your calculator to find the ratio. So let's see whether we are going to have a common ratio. So the ratio between the first and the second term, you are going to get 1 over 2 divided by 2, and that will be times 1 over 2. Am I right?
Yes, please.
Okay, so which gives us 1 over 4. Do you agree?
Yes, please.
Okay, then we are going to get 1 over 8 divided by 1 over 2. So it will be times 2. Okay, which also will give us what? 1 over 4. All correct. So you can see that the ratio, okay, here, basically common, the same ratio. So we have what? A common ratio R. So now we know our R. So that's your rough work, you cancel it. So in this case, I will come and quote. So let me find out whether the sum to infinity will exist. So my R is equal to 1 over 4. So it means absolute value of R will be equal to absolute value of this. So absolute value of R will be 1 over 4. Am I right?
Yes, please.
Okay, so is 1 over 4 less than 1?
Yes, please.
So it means, will the sum to infinity be possible or it will not?
It will be possible.
It will be possible. Very good. So now what do? We go and write, okay, therefore, okay, or I can write maybe sum to infinity. Okay, is equal to, I'll quote the formula first, A over 1 minus R. I need my A and my R. So I'll write, okay, but my A, okay, what is the A here? A very pretty number, which is what? 2. Okay, and your R, we found R when you were investigating the nature of this word sequence, and we got R to be equal to 1 over 4. So we are in a comfortable league. So therefore, okay, the sum to infinity will be equal to A, which is 2, over 1 minus 1 over 4. So we are going to get, okay, 2 over, okay, I am going to use divided by, then it will be over 1 minus 1 on 4 will give us 3 on 4. Am I right?
Yes, please. Yes,
okay, which in effect gives us what? 2 times what? 4 on 3. Okay, so that gives us 8 on what? On 3. Am I right?
Yes, please.
But you know, assuming this didn't go here, let me check whether I have a next page. Okay, I have, so I will continue here. Okay, so that will be equal to, remember, we don't conclude with an improper fraction unless otherwise stated. Okay, so in this case, you change this one to its corresponding base numbers, and that will give us what? 2 whole number, 2 on 3. Am I right?
Yes, please.
Okay, so 2 whole number, okay, 2 on 3 must be your answer. Afa.
Yes, please.
Okay, great. Okay, so we have, okay, C. Let's look at what C will equally give us, and that's of the D. When this is because we'll be using this often based on what we are going to do. Okay, a lot of sum to infinity questions that we work on. So this being the first one, I have to make sure that we are all fully grounded. Okay, for us to, deeply rooted for us to deal with the rest of the questions. So let's look at the C together. See, what are we giving the sequence? 1 over 2, okay, 1 over 4, then ellipsis, an infinite sequence. Okay, so we are finding the sum to infinity of this. Okay, so let's check whether it will be possible. Okay, this is a GP. Let's see, because we are going to get, okay, the first ratio will give us 1 over 2 divided by 1. Okay, and that will give you, so it's 1 over 2 divided by 1, which we know is 1 over 2. Then we are going to get 1 over 4, okay, divided by 1 over 2, which we know it will be 1 over 4 times 2. So that will also give us 1 over 2. Am I right?
Yes, please.
Okay, so do we have a common ratio?
Yes, please.
Okay, great. Okay, so now what do? We are going to have, okay, it states that this will be indirectly our R. It's our rough work. So how will you indicate that that's your R? Okay, would be okay. So now what do? We are going to start, okay, by dealing with it this way. As usual, let's see whether the sum to, this is a GP, all right, but not all GPs will have the sum to infinity to be possible. So let's see. Okay, R we know is equal to 1 over 2. Absolute value of R would be what? Absolute value of 1 over 2, which will give us 1 over 2. So obviously this is also less than 1. So the sum to infinity is possible. So our right sum to infinity we know is given by A over 1 minus R. So but I know my A is equal to 1 in this case, and my R is equal to 1 over 2. So this happens to be your rough work, strike it out. So what do? We are going to get, therefore, sum to infinity will be equal to A, which is 1 over 1 minus 1 over 2. Okay, so we are going to get 1 divided by 1 minus half will give us half. So that will give us what? 1 times 2, which gives us what? 2. So the sum to infinity 2. All correct. Is my point well made?
Yes, please.
Okay,
Yes, please.
great. Okay, so the last one, okay, and this one, the E will be for you. Okay, so maybe you will try. Okay, I will ask you to try then tell me what you had. So the D, okay, what are we giving? The sequence will be 1, -2, 4, okay, -8, okay, then ellipsis. Okay, so let's see whether there exists a common ratio. Then after that, we'll check whether the common ratio value, okay, will permit, okay, the sum to infinity. So we are going to get -2 over 1, the ratio, and that gives us -2. The second one will give us 4 over -2, and that gives us -2. Okay, the next one will give us the next ratio, -8 over 4. Okay, and that gives us also -2. So we have a common ratio. Do you agree?
Yes, please.
Okay, so let's see whether this common ratio will make, okay, the sum to infinity possible. So our common ratio we know is equal to -2. Absolute value of, okay, R will be equal to absolute value of -2. So what will absolute value of -2 give us?
2.
2. Okay, so if it is negative, it will come outside, okay, out of the absolute value as positive. If it is positive, it will still come out as positive. So 2. Now, is 2 less than 1?
No, please.
No. So the condition for sum to infinity to be possible is not satisfied. So here you write, therefore, sum to infinity is not possible. Okay, if you like, you can attach your reason. Since, okay, R, which is equal to absolute value of R, which is equal to 2, okay, is greater than 1. Is that clear? Because it should be less than 1. Is that okay? Is my point well made?
Yes, please.
Sure. Is everyone on board? Who wants me to go over and from where? Those of you waiting for this question. Oh, sure. Are we all fine, my professors? Are you sure we are all fine?
Yes, please.
Okay, very good. So if that's the case, we are going to do more of the sum to infinity. So let's look at the next question. However, maybe with this one, we'll do the other one. It's basically the same question that I put it in a different form. Okay, so find the sum to infinity of the following, if possible. The sum to infinity of the following, if possible. What you have here, okay, do you see a sequence here? What do you directly see? Especially those who were with us this morning. A series, why?
Because of the plus sign.
Very good. Okay, so you can see we've linked our terms, okay, with the plus sign. So this is a term plus this term plus this term. So whenever you do that, then you move from what? The sequence, okay, to the series. So you know, like I told you this morning, okay, every series contains a sequence, and every sequence we can have its what? Series. So take note of that. So you are asked to find the sum of this what? Series. Okay, and it's a sum to infinity because the series that you have here is an infinite series. So even if you were not asked to find the sum to infinity of the following, if possible, and you were asked to find the sum of the, I could have put the question this way, find the sum of the following series. And you can see that you are dealing with an infinite series. So you are finding the sum of an infinite number of terms. So it will be sum to infinity. You get the point?
No, please.
Okay, anytime. Okay, remember this morning I told you that what do we mean by S sub 2? Those of you who were with us. S sub 2 means, remember I said in general, S sub n means what?
Sum of first divided the first two numbers.
Sum of what?
The first two terms.
Sum of the first two terms. So in general, this is sum of the first n terms. So if I'm looking at S sub 2, then that would be U sub 1, my first term plus what? My second term, because I said the sum of the first two terms. The first two terms will be the first term and the second term, so you sum. Okay, so that's what you have there. So if, let's say I have the sequence, let's assume I have the sequence maybe 2, okay, 4, 6. If I write this one as 2 plus 4 plus 6, okay, I'm looking at this a finite sequence. So I'm looking at the sum of the terms of the sequence here. Is that not it? And the terms here, I have 3 terms. So what I have here is S sub 3. Do you agree?
Yes, please.
Okay, now again, assuming maybe I bring ellipses here. Okay, now originally my sequence was finite. After bringing the ellipses here, it becomes infinite. But do you agree with me?
Yes, please.
So if I am writing plus, I write plus ellipses here. You can see that what I have here, okay, I don't know the number of terms. So whatever that I have here, I am summing, okay, the terms of the sequence here. How many times? Infinite. So finding the sum of the first, okay, you don't know your n, an infinite number of terms. So that gives us the sum to infinity. That's the notation. You get it?
Yes, please.
So what you have here, okay, you can see that what you have here, okay, is we are representing that by what is the sum to infinity? So 4 pluses plus what? Ellipses. So this is the sum to, remember this is an AP. The sum to infinity will not exist. So that one, I'm just using it to drive home my point. So don't get it twisted. Okay, now if I take this part, okay, alone, you remember we said this is sum to infinity. If I take this part alone, we said this will be, what do you call it? Series. Do you agree?
Yes.
And it's coming, this series is coming from the sequence that we have here. And because the sequence, remember I told you, once the sequence is infinite, the series formed out of that will also be an infinite series. So this will be an infinite. So if I give you this, assuming I give you this, and I ask you to find this. If I ask you, the question says, find this. Indirectly, you should know that you are summing a number of terms infinitely. So that means you are finding sum to infinity. You get it?
Yes.
Yes,
Okay,
please.
so that's exactly what I said. So what we have here is coming from the sequence 2, 1 over 2, 1 over 8. Because it's out of this sequence that we put plus there to form the, so let me bring my ellipsis, to form the infinite, okay, series. Do you agree now?
Yes.
So even if the question didn't say, find the sum to infinity of the following, and the question just said, find the following, you should know that what you have here, you are looking at sum to infinity. Is my point well made now?
Yes.
Okay, so I was just walking you through how you could be tricked. The question usually will not be the direct way that you have it there. Another possible way of framing the question. So please take note. All right, so let me see. You see somebody's, okay, is giving us, okay, so let me mute. All right, okay, so at this point, we are good to go. Let's go and have a look at the solution once we understand the import of the question. So let's go and look at how best to deal with this. So like I said, indirectly, we've done that. So you are looking at the sum to infinity. So question 2, okay, A, what are we giving? We are giving 2 plus what? 1 over 2, okay, 1 over 8, okay, comma, oh, sorry, it's plus ellipsis rather. It's not, we are forming the C, so you extract exactly what you have there. So plus your ellipsis. So now we agree that what we have there, obviously we are dealing with series. And out of every series, we can get the corresponding sequence. So if you know how to find the sum to infinity of sequences, you should be able to find the sum to infinity of series. How far?
Yes.
Okay, so let's see. Okay, we know for the sum to infinity to exist, your ratio, your common ratio must satisfy a particular value. So because the sum to infinity will give us a part. So in this case, I'm going to write, okay, sum to infinity. So what we have here, okay, which will be equal to, here, sum to infinity we know, will be equal to A over 1 minus R. Is that not it? That's the formula. Okay, so in this case, what do we have? Let's go and fast for A, we know the A will be 2. Then what we have here, this will be, okay, what we will use to find our ratio. So the first ratio we are going to get what? 1 over 2, sorry, forgive me, divided by 2. And that will give us 1 over 2 times 1 over 2, which will give us what? Okay, 1 over 4. Remember, we've done this. Okay, the same question that I have put it in the series form. So the other one too will give us 1 over 8 divided by 1 over 2, which will give us the ratio, okay, 1 over 4. So we have a common ratio, okay, and that common ratio, absolute value of that will be less than, okay, 1. So in that case, you can say that what we have here will be equal to. So I'll write, okay, therefore, what I have there will be equal to, okay, so but A is equal to, okay, 2, and okay, my R is equal to 1 over 4. You go and substitute. So I'll write, therefore, sum to infinity, what I've been asked to find here will be equal to, okay, 2, which is your A, over 1 minus 1 over 4, which will give us 2 over what? 3 on 4. Okay, which in effect will give us what? Okay, 2, okay, times 4 on 3. Am I right? Which will give us 8 on 3. You change it, and that was the one that gave us what? Okay, 2 whole number 2 on 3. So the sum to infinity will give us what we have. Is my point well made, my professors?
Yes, please.
Okay, great. All right, so Now, if that's the case, then we are more than good to go. Okay, all right. So now let's see what we are going to get for, I think with this, you should be able to find us. Okay, it's the last one that we didn't do it for the other one. That we involve. So let's first of all find out whether there is a common ratio here. So I will go back and see because I formed this one from this particular one. Okay, just as the rest, I picked some of this and I think I started from here. I picked and used that one to form. So let's see. Okay, so check whether, okay, find a common ratio here. If there is a common ratio, find a ratio for this one for me. Okay, and let's see. So let's do that together and see. Okay, R for the first one will be, I'm looking at the E. Okay, I'm doing the R. So R will be 1 over 2, 1 over root 2, forgive me, divided by, okay, 1, and that will be equal to 1 over root 2. Am I right? Am I? Okay, but you know,
Yes,
well, I thought you said, okay, instead, you cannot end with this as your answer. You know, okay, that you shouldn't leave your final answer to contain a set in the denominator. So mentally, we can rationalize this. So that will give us the numerator times 2, the denominator times 2. So you are going to get root of 2 over 2. Okay, even your calculator can help you. Feed your calculator with this and press equal to. This is just your rough work. Rough work shouldn't be very detailed. Okay, so you can skip certain steps. Okay, or we could have used our calculator straight away here, and the calculator would have given you this. Is my point well made?
yes, please.
Then let's go and look at the second ratio. So you are going to get 1 over 2 divided by 1 over root of 2. So we know that that will give us indirectly. Okay, we are going to get 1 over 2 times root 2 over 1. So which will also give us root 2 over 2. Am I right?
Yes, please.
So there exists a common ratio, only that the common ratio is not pretty, but it's still a common ratio. However, let's see whether this common ratio, okay, satisfy the condition for us to find the sum. So it's root of 2 over 2. Use your calculator. Your calculator will give you decimal, and you can easily use the decimal to draw your conclusion, whether it will be greater than 1 or less than 1. Root over 2 over 2 will give you the decimal.
0.707.
So once you see 0 point, then obviously you should know that it's less than 1. Is that clear?
Yes, please.
Okay, so let's see if you can find the sum to infinity. Okay, here. So I am going to do it for the other one so that once I do it there, then it covers this one. Is that okay? So I will skip this process when we are looking at the other one, okay, because we know our R now. So I am going to look at, okay, the D straight away from here. So D, okay, we've been given 1 plus 1 over root of 2, okay, plus 1 over 2 plus ellipsis. So we are finding the sum to infinity. Okay, you have your terms there, so series. Okay, so now what do we have? We know what are we being asked to find the sum to infinity. Sum to infinity we know is S sub infinity is given by A over 1 minus R. Okay, so here we know we have found our R. So we did the rough work there. So the R, remember we said gave us root of 2 over 2. Am I right? Okay, Prof. Karen. Prof. Karen, your hand is up.
Before you get the decimal, can you like change the decimal to a fraction?
Oh, you see, the purpose of the decimal that you have there is for you to determine, for you to, I mean, for me, immediately I see this, I will know, because of maturity, I will know that the number that you have here is less than 1. Okay, I asked you to change it to decimal for you to obviously see that this is less than 1. Otherwise, that wouldn't be necessary. You get it? I know root of 2 will be smaller than 2. So a smaller number being divided by a bigger number, obviously my result will give me less than 1. You get it?
Yes.
So I wouldn't do that, but because I wanted you to clearly know and see that root of 2 over 2 is less than 1, that's why I say change it to decimal. So if you change it to decimal, you see 0 point something or negative 0 point something, then you know you take the absolute value. So it will be less than 1. Is that clear?
Yes, please.
Okay, so I can work with this. So in this case, I'll write, but my A is equal to 1 and my R, okay, is equal to root of 2 on 2. Okay, so in this case, I'll write, therefore, my sum to infinity will be equal to A, which is 1, over 1 minus what? Root of 2 over 2. Okay, so you know what is going to happen here. It's just a little, because this fraction here is not that pretty, and you cannot easily get, okay, the result of your denominator here mentally. You have to go through a certain step. So we are going to get this to be equal to, let's do that. I told you, you can use your calculator at this point, but when it involves says, I will plead with you, do it, okay, this way. So in that case, we are going to get 1 divided by, then you take the LCM. So that will give us 2. This is over 1. So 1 will go into 2 times 1. So you get 2. Then minus, this will go here, so it will be root of 2. Is that clear? So look at what is going to happen here. A little more work here. So we are going to get 1 over any number over a fraction. I mean 1 over any fraction. Okay, we'll give you the reciprocal. Is that clear? So I know that what I have here will give me 2 over 2 minus root of 2. All correct?
Yes, please.
Okay, can we end here?
No, please.
Okay, we can, but we shouldn't if you cherish marks. Because remember, you don't leave a third containing a third in the denominator. Alpha. So this calls for what? Rationalization. So you can see we are doing sum to infinity. Someone may ask, okay, what is third doing there? So that's why I always tell you in maths, you don't choose and pick the topics that, okay, like. Okay, you should like all the topics. However, it is, okay, allowed for you to love, okay, some of the topics. Okay, so in this case, I don't end here. I need to go and rationalize. So I'll write this again. Then how do I rationalize? Make me proud. So times
2 plus root 2.
the conjugate 2 plus root 2. Okay, so let me do that. 2 plus root 2. Very good. Okay, so it means you've not forgotten your sets. Okay, so at this point, if you have forgotten your set, that's where you end. Okay, if you use your calculator, you will lose the marks. Okay, so you are going to get root 2 minus or plus root of 2 all over 2 plus root of 2. So let me continue here, assuming this my next page. So I'm going to get this to be equal to, okay, 2 times this, then 2 times this. So that will give me 4, okay, then plus 2 root of 2. Okay, all over. Remember this we said, if you multiply, you always get difference of 2 squares. A third times its conjugate. So you get 2 squared. I told you not to go and distribute. Minus what? Your root of 2 squared. Okay, so this gives us, okay, 4 plus 2 root of 2 all over 2 squared we know is 4. Minus root of 2 squared, okay, is what? 2. So we are going to get 4 plus 2 root of 2. My professors, are you following? All over 4 minus 2 is 2. Okay, can we end here?
Yes, please, but we won't.
Why not? Okay, so now you know. Okay, remember I told you, though you are supposed to leave your answer as a single fraction unless otherwise stated. Check whether you can factorize the numerator to or the denominator to cancel anything there. And you know that 2 is a factor of 4, it's also a factor of 2. So it means you can factor out 2, okay, and what? Cancel. So if you do that, it will be 4 over 2, which will give us 2. Then this over 2, which will give us plus root of 2. So you end there. Is my point well made?
Yes, please.
Okay, so as simple as that. Okay, so here, instead of, so sometimes, okay, the question like this, maybe if I want to test your concept of, or on the third, rationalizing the denominator. Instead of giving you this straight away to rationalize, okay, I can start the question this way. At a point, you will get this and you will know whether you know how to rationalize or not. Afan, any questions at this point? We are still on sum to infinity. Okay, so at this point, okay, we are going to hold on and have our water break. Okay, so please, I'm giving you about 5 minutes, okay, for your water break. Okay, so welcome back from your water break. Okay, so quickly, we are going to look at our worked example 3. Okay, so let's study the question, get the import of the question. Understanding the question is part of the exams, as we always say. So let's get the full understanding of the question before we start dealing with it. So express as an infinite series. Okay, so we are supposed to first of all express what you have there as an infinite series. And hence, remember I've told you anytime you read, okay, question and you see hence, underline hence, find the sum of the geometric series. Okay, so hence we need to find the sum of the series. So obviously, because the series that you have there will be an infinite series, if you are finding the sum of the series, okay, it will be the sum of an infinite series, which will be sum to infinity. All correct. However, that is not all. Remember, I told you, you are not done reading the question. Leave your answer in the form. So the second part of the question, you need to find the sum of the geometric series, all right, but not, okay, that's only. We are supposed to leave our answer in the form. And I've told you in maths, anytime you're asked to leave your answer in the form, whenever you read it, you underline. All correct?
Yes, please.
Okay, so we've done the needful. Let's see how best we are going to, or we are supposed to deal with this question. So let's go and look at the solution. At this point, I will need your utmost, okay, attention. Okay, it's not going to be that. I know, you know, when you were, I think, yes, in core maths, you did expressing, okay, rational numbers or recurring decimals as rational numbers, right?
Yes, please.
So
Yes.
if because of the preamble, we cannot use that technique. So if the question was just express, okay, this in the form A over B, then someone can use the series, okay, approach, which is the series and sequence approach, or use the format approach, which is the let, okay, you let S to be equal to this, then you know the steps, but that's not the approach that we are looking at. We are looking at it from the sequence and series perspective. So take note. If you like, after that, go and do the other one. You end up getting the same result. However, in this case, if you do that one, okay, you know, the question said, first of all, express it as what? As an infinite series. If you go that approach, you will not express it as an infinite series. One, it will not be expressed as an infinite series, irrespective of the steps that you go through. Then two, hence. So hence means use previous results. Your hence will not come in. So it means if you use that approach, 0 automatically. So please take note, okay, of that. All right, okay, so that is the approach that we are going to look at from the sequence and series approach. Okay, so now let's look at the best approach. Okay, so after reading the question, you've underlined the salient part from that question. If you like, you can equally do same here. Hence, this is the second part. So the first part, infinite series, hence, then the form. You must underline this. Okay, so your solution must meet all that you have underlined. So question 3, okay, A. Okay, what are we giving? We are giving, okay, 0.3 recurring. Can you see that it's 0.3 recurring?
Yes.
It's not just 0.3. It's 0.3 recurring. Okay, so this is what you do. Okay, it is so easy. Okay, what we have here, okay, we can write it. I'm going to write it in another form. Remember, there's an expression. So if you start with equal to. So we are now going to look at it from the infinite series, okay, perspective. So we are looking at it from the first part of the question before we come to the ends. Okay, take note. So in this case, I am going to get 0.3 recurring is the same as 0.3, okay, you don't end there, plus, okay, 0.03 plus 0.003, then plus ellipsis. Continues in that part. Should I come again?
Yes, please.
Okay, all right. You know 0.3 recurring is the same as 0.3333 ellipsis. Is that not it?
Yes, please.
Okay. So what you do is the first one, you take the first one. So the first one will be 0.3. So you write it. Plus, if 0.3 is taken out, then you know that the next term, this will go and this will be represented by 0 because this has gone. Is that okay?
Yes, please.
Okay, so you are going to replace the whole of this by 0.0. Then your next 3 will come. So the next one to the whole of this is gone. You are left with, so you place this one with 0.00, then your 3 will come. So it means the next term, if I were to write it, it would have been 0.0030, then 3. You get it?
Yes, please.
So once you get the pattern this way, okay, so you know, I don't think you wanted me to hear the no. So I intentionally, okay, I intentionally didn't hear. All right, okay, so no problem. Okay, so you understand 0.3 recurring. That's the form. It means the 3 repeats itself, okay, without, okay, bounds. In that, so is that clear? As for that one, you understand it, is that not it?
Yes, please.
Okay, so I said, okay, indirectly here, I'm just helping you. Immediately we say an infinite series, then it means you are going to get terms that you are supposed to add. You get it?
Yes, please.
Remember, for us to get series, there should be terms, okay, which will form our sequence that we'll add. So what will be our first term? And I said the first term will be 0 point your normal without the dot on top. Okay, plus, okay, as you move, you keep on replacing the number that you have there by 0. So it will be 0.03. The next one, to replace this one by 0, and you introduce the next 3. You get the point? Because if I take the first 2 and I want to write it, only the first 2, you can see that if I add, I am going to get 0.33. You get it? If I come and add the third one too, I'll get 0.333. Is that okay?
Yes, please.
If I add the next one, it will give me 0.3333. So it means, you know, I am in that because it is infinity, then it means I can bring my ellipses there. Afa, the person who said, okay, no undertone. Okay, I want your ears to be, okay. Okay, so are you fine?
Yes.
So you just need to know the pattern here, that is all. If you know, and I'm giving you the trick, that's all. So it means if I gave you 0.5 recurring, then it will be 0.5 plus 0.05 plus 0.005. It's only one number recurring. So that's how you write it. We'll come to a situation where you have 2 numbers. So here, this is what you have. Okay, so let's stick to the first explanation. As you move on, you know, that's my style. I will give you, okay, whatever that you need. Okay, which definitely will be an upgrade of this information. Okay, so I'm letting you know indirectly from the simple to the complex, sort of. Okay, so if that's the case, then I think this can go. So you can see that what we have here indirectly is the series, okay, of what we have there, the infinite series. So in effect, I can draw my conclusion for the first part of the question. Okay, so indirectly, I'm going to do that, but let me clear this so that, okay, I don't need this, we are matured. So we wouldn't need this. Okay, and this one as well, I only use this one to dump home my points. Okay, so at this point, we are more than good to go. So if you are with me, then I can say the first part of the question was 2 in 1. So first part of the question, I draw my conclusion, all right? Therefore, okay, my 0.3 recurring in terms of an infinite series will be 0.3 plus 0.03 okay, plus 0.003. In every sequence, the first 3 terms will be okay. Okay, so in the same way, in every series, the first 3 terms will be okay. Don't forget to introduce your plus ellipsis, because we said it will be an infinite. If you end here, then what you have there, you've written that as what? A finite, okay, series. In any case, that would have given you 0.333, okay, but that is not the same as 3 recurring. Okay, the 0.33, okay, without your ellipsis, truncates, okay, however, or terminates. However, 0.3 recurring does not terminate. So please take notes and know the difference. Okay, so the first part of the question, Claire, do you agree?
Yes, please.
Okay, so now going forward, we are going to look at the second part of the question. The second part of the question says, hence, we need to find the sum of the geometric series. So your geometric series that you have here is this. Okay, this is obviously, you know that this is a series. So we are finding the sum to infinity of what we have here. So indirectly, I am finding the sum of the geometric series will be sum to infinity. Okay, and that we know will be equal to A over 1 minus R. Do you agree? Please, are you following? I can feel within me that some of you are not following, but you are just quiet. Okay, please, you know, okay, you know that the afternoon is very hot. You cannot, okay, sacrifice your afternoon and you wouldn't get anything here, please. Make sure if you have issues, let me know. We are all not going back the same, we'll go back better. All right, so now in this series that you have here, obviously we can find the first term, okay, and what the common ratio and see whether we are going to get the common ratio to give us. But usually, I will advise that at this point, if you like, you can choose not to work with the decimals. But if you want to work with the decimals, it's allowed. No issues about that. Only that because the question asks us to leave our answer as a fraction, not as a decimal. If you work with decimal, at a point you get the decimal, you have to change the decimal to a fraction. You get the point?
Yes, please.
Okay, so let's work with the decimal. Okay, we'll deal with it with the decimal approach. The second one, I will deal with it from the fraction approach from the beginning so that our answer straight away give us a fraction rather than a decimal, okay, number. So now, in this case, I need to go and find my A and R. So, but I know my A, as for A is known, that is 0.3. Do you agree?
Yes, please.
Okay, so let's go and find our R. Okay, obviously we know always, okay, once you know that this is going to be a geometric series, okay, but let's find it, our R here. Here we are going to get 0.03 over 0.3. Use your calculator to give me the value. I'm waiting. Then the other one will give you 0.003 over 0.03. As your rough work, I'm waiting, my professors.
Please, you want the answer in decimal fraction.
Okay, because you worked with decimal, I want the answer in decimal.
Okay, the first one is 0.1.
Okay, 0.1. The second one, 0.1, obviously. So we do have a common ratio. So in this case, you write, and R is equal to 0.1. Do you all agree?
Yes, please.
Yes.
Okay, so in that case, okay, if you like, even in this case, you can choose not to write, okay, sum to infinity. But our conclusion will draw the conclusion correctly. So don't take, I have not concluded. So in this case, I will not conclude with sum to infinity. Okay, because the question didn't ask me to find the sum to infinity, though it's indirect. The question asked me to take this one rather to that form. So I will conclude with the 0.3 recurring. So take note. So in this case, I'll write, this implies that sum to infinity will be equal to A, which is 0.3 over 1 minus, okay, 0.1, which is your R. So that will be equal to, so here I'm waiting, 0.3 over 1 minus 0.1 will give us what? 0.9.
1/3.
Okay, so 0.9. I want this in decimal. Is that not it? Okay, but you know.
0.33.
Come again.
You said you wanted the answer in decimal.
No, I don't want the whole of this. I wanted only the denominator answer in decimal.
Okay.
1 minus 0.1, which will give us 0.9. Do you agree?
Yes, please.
Okay, so now you come and have, okay, this one, you take this one to its corresponding fraction because the profession asks us to leave it in the form of a fraction rather than decimal. Okay, so here, this is what we are going to do. We know how to, so we've all done standard form. Okay, otherwise you can use your calculator. So use your calculator to do 0.3 over 0.9.
1/3.
Okay, so 1/3 is what you have here. So at this point, I'm going to draw my conclusion. So my conclusion will be therefore, so I was asked to express this one in that form. So 0.3 recurring will be equal to 1/3. Do I end here?
Yes.
Okay, I can end here, but I shouldn't. Remember, I told you anytime the form contains unknowns, always compare and attach the values. So if you compare, A will be equal to 1 and B, okay, will be equal to 3. Remember I said this?
Yes.
Okay, so take note. The rules basically the same. Okay, so don't be victim to some of the petty maths that or trash that we set for you. Okay, is my point well made? This is the first example. The second one, maybe I will handle it a little different and maybe more maturely or ideally. However, before you move on to the second one, any issues? Oh, we are all fine. You are doing well. Keep it up. Okay, if only you are not hiding, okay, your issues. So let's go and look at that of the B. Okay, so B, this time around, we are going to deal with it maturely. B, what are we giving? We are giving 0.7 recurring. Okay, so we know this will be equal to, okay, help me get the decimal form of this in terms of series.
$0.7.
Okay, so I know whatever that I'm going to write, okay, will land me at my answer. So at that point, I can have my conclusion drawn for the first one, or I can even write therefore here. Is that okay?
Yes, please.
That's the first part. So let's go. 0.7.
0.07.
No, you won't write anything. You just write
plus
plus.
0.07.
The whole class, I want you to talk. Let me know that you understand. If you understand, unmute and let's go.
Plus 0.007.
Okay, 3 terms, okay. It's okay, so you end there. Is that okay? What 4 and more terms can do, 3 terms can equally do. So just write the first 3 terms of your pattern. Is that clear?
Yes.
Okay, so the first part of the question. Okay, I was expecting you to draw my attention to something, but you have not. Maybe hopefully it will come. If you don't, I will not. Okay, as for those who have joined us, okay, that one, I don't have any issues with you. But my old disciples, okay, at this point, okay, there is something that from the previous one, the A, okay, there is something that we should have written. Okay, Prof. Christine.
It's not about like what we should. I have a question.
Okay, don't worry. I also have an answer. Go ahead.
Please, the first one, like after we solved everything and we got, it was equal to 1/3. Why is 0.3 equal to 1/3?
No, it's not 0.3, it's 0.3 recurring. There is a dot on top. You get it? So it's not 0.3. I said it from the beginning. There is a dot on top. So it's 0.3 recurring. So if you like, take your calculator, Do you have your calculator with you?
Yes, please.
Okay, and this is how you can verify whether the fraction there represents the recurring decimal. Then punch 0.33333 until you see on your screen, you see your 3 moving, or whatever you are typing or punching, moving, then press equal to. It will give you the fraction form of that. Then you can use that to verify whether you are right or wrong. Have you done that? So 0.3 recurring means 0.3333. So press then, when you see it moving on your screen, okay, then you press equal to. Christine, have you done that? Prof. Christine.
Yes, please. 1/3.
So you can see that we are not wrong. We are right. Okay, so
Yes,
if it's an objective question, then you are good to go. Okay, but subjective wise, okay, you can only use your calculator to verify.
Yes.
Okay, which we have. Okay, Prof. Liz.
Ms. Akman, please, at the end it said we should and hence find the sum. So it shouldn't be therefore, it should be hence.
I know, definitely. So you can't conclude. The second one, you can't conclude with therefore. You are supposed to conclude with hence. Okay, that was what was missing. Okay, this should have been hence. You know, okay, I am very consistent. So, okay, so if I only see inconsistencies in your, no, I will take note of that. Okay, I've told you the experience that I have. Okay, some of these things, I know all the tricks in the questions, all the notes. Okay, so I will let you know as well so that you don't fall victim. Okay, or you are not ensnared by those traps. Okay, all right, so thank you very much. Okay, Prof. Liz. Okay, so at this point, we are done with the first one. So hence, we are going to the second one. Okay, so in this case, okay, somebody can write hence here straight away. Okay, or I will say that, hold on, in your final conclusion, then you write hence. Okay, I think this one is looking like there is no E, so let me write it well. Hence, okay, 0.3 recurring, not 0.3, the recurring is here. Okay, so now this is what we are going to do. At this point, we know we are in a comfortable lead. So I will know that what I have here, I'm looking for sum to infinity. So I'll write sum to infinity, okay, will be equal to A over what? Over 1 minus R. Okay, so my A, instead of going for the decimal, all the decimals that I will get, I will take it to their corresponding, okay, fraction, then work with the fraction, as simple as that. So in this case, I'll write, but my A is equal to 0.7, and 0.7 is the same as what? 7 over 10, do you agree?
Yes.
You let me write
Yes.
0.7, which is equal to that, so that, okay, you can easily relate. Okay, but once you mature, you can choose not to write the 0.7 before. Okay, or let me even write it this way so that you can relate. Okay, then we move from there. At this point, if you are matured, so let me come in. Okay, so we are good to go. So I can write this one as, okay, 7 over 10, okay, plus 7 over 100, okay, plus 7 over 1,000. Do you agree?
Yes, please.
Then plus your ellipses, so that you can easily work with the fractions. Okay, so if you want to work with the decimals, you go here. If you want to work with the fractions, you look at this one. Safa. Okay, so now sum to infinity, we know is equal to A over what? 1 minus R. Okay, so in this case, I know I'm not finding sum to infinity. So only that, I mean, indirectly, I'm finding sum to infinity. Okay, so let's see how we can handle it maturely. That's what I said. Okay, so I'm assuming you have matured. So let me do the writing, forgive me, in terms of the presentation. Okay, so let's go and look at it from this perspective. However, if you can relate with this one, just go by that approach. So I can write, let me write hence, yeah, okay, hence my 0.7 recurring, okay, I know will be equal to, okay, we know it will be A over 1 minus what? R. So it will be A, which is 7 over 10. Okay, I'm quoting the formula, only that this time around, I'm quoting the formula with specific values. Here, I quoted the formula in general. Okay, then it will be 1 minus, I need to go and find my R. And your R, you can do it as your rough work. So take this 100, 1 over 100, okay, times, okay, 10 over 7, or divided by 7 over 10. Give me the value, I'm waiting. 0.1.
Yes, please.
Okay, so I am going to get my R will be 0.1. Okay, so by then you have done your rough work and you know that your R will be 0.1, you know. Okay, divided by that. So at this point, I'm now going to work with what? Okay, fraction. So it will be 7. Hey, did I say 0.1? Change it to, I'm working with fractions. Okay, so change it to its corresponding. So 1 over 10, Abby.
Yes.
Okay,
Yes.
so inconsistency in my presentation. So 1 over 10, sorry. Okay, so in effect, I'm going to get 7 over 10, okay, divided by, this will give us 9 over 10, all correct?
Yes, please.
Okay, which in effect will give us 7 over 10 times 10 over 9. So that will give us what? 7 over 9, am I right?
Yes, please.
Okay, however, remember, hence here, so what I have here is already, okay, a conclusion. So I can write my comma, compare. A will be equal to 7 and my B is equal to 9. Afa?
Yes.
Okay, so you can handle it maturely this way. And remember with this one, if you did this, remember this your rough work, don't forget to strike it out. Okay, this one too, you come and do this for your R. As your rough work here, you strike it out. As simple as that. Safa. Okay, all right, so now we are going to look at a situation. So let's look at it. Yes, please. I'm here, my prof.
So what if you use the decimal
For each of them
use the fraction?
from here?
Yeah.
Yeah, I said that's why I've given you 2 ways of dealing with it. If you want to work with the decimals, you can work with the decimal, only that you cannot end with the decimal because of the nature of the form. You get my point? So, and I said, here we worked with what? The fraction. So it means our answer will land at the fraction straight away. We don't have to convert from decimal to fraction when we start working with the fractions.
Okay.
So if you work with a fraction from the beginning, your answer will be fraction, which is what is expected of you. But if you work with a decimal, okay, at this point you will get, okay, you will get what you have here. Okay, this will be a decimal, this will be a decimal. And if you use your calculator, maybe your calculator will give you the decimal form of this. Okay, then you change it to what? Its corresponding fraction. Otherwise, you write it. Yes, please, I'm here, my prof.
So I did it. And I used the
this one, you didn't get the answer.
I used the decimal.
Did you get the answer? Hey, Ken, is that you?
Yeah.
Okay, so did you get the answer?
Yeah, I got 7 over 9. I changed it to 1 decimal.
So it's allowed. Okay, remember I always give you, and obviously you can see that I said this is the ideal way of looking at it, because if you look at what we have been direct. If you work, and I even said it along the line, I told you that if this approach sits well with you, go for it. Because it's usually better to go use the approach that you are comfortable with rather than the ideal. Only that I will always advise you to go for the ideal. But if the ideal, you know, you are not mature, you force yourself to be mature, then you lose the marks. Do the other one and protect our marks for us. Only that when you are using the other approach, you have to be fast in your writing. Okay, all right. Okay, so please, are we all fine? Can I move on at this stage?
Yes.
Okay, very good. Okay, so now let's see what lies ahead. Okay, in terms of, so the next question, I think, let me move this one from here. Okay, so I can. Okay, take it. Okay, so let me bring it here. All right, so this is what we have. Okay, so the next one, you can see that the first two examples that we have there, your recurring digits, okay, come immediately, the digits that you have here. Or let me even say this one, the recurring digits that you have here comes immediately after the decimal point. Can you see that? But with these two, okay, your recurring digit is not directly after the decimal point. You have another digit, okay, before, okay, your recurring digit. You get the point. So your approach here basically will be the same, okay, but how you place this one in terms of what the decimal, I mean, in terms of this, okay, is equally critical, and it will be a little different. So let's see how we can easily, okay, do that. Point well made. Okay, I think I should have taught you where you have two recurring digits before coming to do that. I didn't arrange my questions, okay, clearly. Let me see whether the next set of questions will have two digits directly after the decimal point. Okay, so I will do this one first. Okay, then when you understand, then we'll look at a situation where your recurring digit is not directly after. Is that okay? I think these two should have joined the other set of questions so that you can easily relate. Okay, so let's skip, okay, or, okay, we are going to shelve these two questions for now. Okay, maybe this one will be for you. So we'll shelve the C for now. Let's go to our next set of questions. Okay, what is important is you grasp all the concepts. Okay, that is what is important. So we can skip that. Let's come and better our understanding in this particular question. So with this one too, we have to express that as an infinite series, and hence, okay, however, here we are supposed to so underline this, and underline the form. The form this time writes x over y. So take note. So quickly, let's go and do the other one and see. So solution. Okay, the first one, what are we looking at? We are looking at question 4, solution to question 4. So let's write 4. Okay, and A. Okay, what are we giving? We are giving, okay, 0.12 with a 1, 2 recurring. Is that clear? So with this 1, 2, you have, so we are still looking at a situation where your recurring digits or digits, okay, come immediately after the decimal point. Immediately, directly after the decimal point. However, here directly, by this time around, we have how many recurring digits? How many?
2.
2. So the previous one, we had 1. So the first approach will be, okay, you know, okay, if it is only 1 recurring digit, we know what to do. So if it was 1 recurring, it would have been 0.1 plus 0.01. So in this case, we are going to get 0.12. Okay, then plus, who can tell me the next, okay, number that I'm supposed, the form of the number, decimal? I want someone to tell me.
0.1212.
No. There should be only 1, 2 in it.
0.0012.
Perfect. Remember, I told you immediately you write your first, when you get your first term right, okay, the rest of the term should be, yeah. Because I told you the numbers that you have here, you replace all of them with zeros, then you write the 1, 2 again. So in this case, I'm going to get 0. This will be replaced with 0. So 0, 0, then your 1, 2 will come 1, 2. Afa. Okay, so if indeed, Afa, let me look at your next term. So plus, okay, I will come down, okay, because I know that it won't go there. So the next one will be, okay, you can put up your hand and tell me, especially the one who had, okay, the second term wrong. Please, I want you to convince me that you've understood. So tell me what's the form of your third term. So it will be 0.00, and this 2 also replaced by zeros. So it will be 0, 0, 0, 0, then you bring your 1, 2. Afa.
Yes, please.
Okay, then plus, don't end there. You know it's an infinite. So plus your ellipses, your 3 dots. All correct?
Yes, please.
Okay, very good. So if you are, okay, fine at this point, then we are good to go. So those of you who want the decimal, I'm going to work with the decimal. But remember the first part of the question, I am going to draw my conclusion. All right, therefore, and I could have ignored this there and written therefore here so that my conclusion would be there. So I'm going to conclude with the decimal. That would give me 0.12 recurring will be equal to 0.12 plus 0.0012 plus what? 0.0, how many 4 zeros? Okay, let me continue here. 1, 2, then plus ellipses. Is that clear?
Yes, please.
Okay, so the second part of the question, we are going to look at the hence. So hence, we want to find the value of this in its fraction form. Okay, this will be equal to, remember we said sum to infinity, so it will be a over 1 minus, so you can quote the formula somewhere, okay, or mentally you know. What is your a? 0.12, all over 1 minus your r, as your r, you know, your rough work. So your r, just you know, this will always be a geometric sequence, always. Okay, so in this case, you just do the first, okay, ratio, and that will give you your r. So that would be 0.0012 over 0.12. So what would that give you? I'm waiting.
0.01.
0.01. So this time right, it's not 0.1. Take note. So your r will be equal to 0.01. So it means I'm going to get 0.01 here. Okay, remember this happens to be your rough work. You cancel it. When you are moving here to from here to your next line, you write close to the margin. So you are going to get 0.12 all over 1 minus 0.01 will give us
0.99.
0.99. Okay, so 0.99. Do you agree?
Yes, please.
Okay, so at this point, okay, you can fall on your calculator. So you cannot conclude here, remember. You cannot leave your answer in terms of decimal. So feed your calculator and let's see whether your calculator will give you decimal. If it gives you decimal, then you know what to do. Okay, you change that one too. So do this and let's see what your calculator will give you. Hey, Prof. Adoma.
4 over 33.
4
over 33.
Okay, do you agree?
Yes.
Okay, but do we end here?
No, please.
So what is left?
Say hence.
A is equal
The hence is already here. Okay, did I hear A? You see, you are caught in the web.
A is equal to
No A. Check. It's no check. I even said it. Look at the variables involved in your form.
X is equal to 4.
Yeah, so comma, you compare. X is equal to what? 4. And, okay, Y is equal to 33. Okay, this cannot be reduced, so you end here. Is my point well made, my professors?
yes, please.
Sure.
Yes.
Okay, very good. Okay, so if that is the case, okay, we are going to do, okay, I think we should do this. Let me give you this one to try. You are trying, okay, here and now. You are doing this one as a classwork. I think we have about 10 minutes. You should be able to do that. Okay, within 10 minutes. Is that not it? You should be able to do that. If you need more time to do it, no issues. Okay, you can submit it later. Okay, I just want you to try. Okay, or just try. I'll call one of you to give me your solution. Then we'll end here. In our next meeting, okay, by then maybe more students will come on board then we'll look at, okay, I'll explain from here and the other questions going, for them also to relate and relate very well. Is that clear?
Yes, please.
Yes.
Okay, so now I am going to pause here. Okay. All right, so at this point, okay, please, you wait. Okay, this will be your assignment, but I'll put it in a better form for you to know, but this will be your assignment. Anyway, maybe I will add one more, okay, question based on what we've done, okay, today. Okay, so thank you very much for your contribution and, okay, making the class very interactive and successful. God bless us all.